Chemistry lecture number 66, Kinetic Theory, Introduction to Boyle's and Charles' Law. A balloon is filled with gas. What are the properties of the gas that give a balloon its size and shape? Kinetic theory makes the following assumptions about the gas inside the balloon. The balloon is filled with tiny, indestructible particles, atoms and molecules. The particles that make up a gas have a very tiny volume. The volume is so tiny that we assume the volume of the gas particle is zero. The particles do not attract or repel each other. Gas particles are in constant random motion. The particles move in straight lines at very high speed. Particles change direction only when they collide with each other or with the walls of the container. No kinetic energy is lost when gas particles collide with each other or with the walls of their container. And these types of collisions are called elastic collisions. If the collisions were not elastic, energy would be lost to friction and a balloon would get smaller and smaller as the particles move slower and slower. So for example, I have a balloon, and notice the balloon is keeping the same volume. And the reason it keeps the same volume is because the atoms and molecules that are bouncing around inside them, they collide with each other, but there's no friction between them. No energy is lost to friction. All the energy is simply transferred from one collision to another. So if there were friction, the molecules would move slower and slower, and if the molecules and atoms in here move slower and slower, there'd be less pressure, and then the volume of the balloon would gradually shrink. But that doesn't happen. So the reason why it doesn't happen is because the collisions are elastic. Energy is just transferred between collisions. No energy is lost. All gases have the same average kinetic energy at a given temperature, and thus a balloon filled with oxygen gas will have the same kinetic energy as a balloon filled with helium gas as long as both balloons are at the same temperature. If one balloon has a higher temperature, then it has a higher kinetic energy and its particles move faster. Kinetic theory explains how the size of a balloon can change as the surrounding air pressure changes. A balloon filled with gaseous atoms and molecules are in constant motion and collide with the inner wall of the balloon. And this pressure inside the balloon pushes the walls outward. However, the atmosphere outside the balloon also exerts a pressure on the balloon. Gaseous atoms and molecules from the atmosphere collide with the outside surface of the balloon. Thus, the atmospheric pressure pushes the walls of the balloon inward. If the size of the balloon remains constant, then the atmospheric pressure pushing inward is equal to the gas pressure inside the balloon that is pushing outward. So here we have a diagram. Here we have a balloon, and we have some atoms and molecules of gas inside here. They're all moving around, and as they move around, they collide with the inner wall, and they create an outward pressure, so it pushes the walls of the balloon outward. But the balloon is sitting in an atmosphere, and the air molecules outside the balloon are colliding with the surface of the balloon, and it presses inward. All right? Now, in this example, the pressure inside the balloon that's pushing outward is going to be equal to the pressure outside the balloon that's pressing inward. And since the pressure inside and outside is the same, the balloon keeps the same volume. So if the pressure outside the balloon is reduced, the pressure inside the balloon pushing out will be greater than the pressure outside the balloon pushing in. The balloon will begin to expand. So here we have a balloon, and there's some pressure inside of it pushing outward. There's some atmospheric pressure pushing inward. Let's say we take the balloon to the top of a mountain where the air is thinner, so there are fewer air molecules and there'll be a decrease in atmospheric pressure. Well, if there are fewer air molecules pushing inward, then that allows the pressure inside to push outward, and the balloon will expand in size. All right? So a balloon that's under lower atmospheric pressure will have a larger volume. Let me adjust the... Okay. All right. Anyway. As the balloon expands, there will be more space inside the balloon. There will be fewer collisions between the gas particles and the inner wall. Internal pressure decreases as the volume of the balloon increases. Eventually, the internal pressure of the balloon will equal the outer atmospheric pressure, and the balloon will stop growing. The internal pressure of the gas is now smaller, but its volume is larger. Thus, if atmospheric pressure is reduced, the volume of the balloon will increase. This is an example of Boyle's law. Boyle's law states that at constant temperature, the volume of a gas varies inversely with its pressure. A gas under lower pressure will have a larger volume. A gas under higher pressure will have a smaller volume. The next time you drive over a mountain range, bring a bag of potato chips with you. As you climb the mountain range, the bag will often begin to swell and get bigger. And this occurs because there are fewer air molecules at the top of the mountain. There's less air pressure pushing against the bag, so the internal pressure in the bag has less resistance, allowing the bag to swell. Kinetic theory also explains how the volume of a gas changes as temperature changes. If the temperature of the gas inside the cylinder that is covered with a piston increases, the atoms and molecules would move faster. And this would cause more collisions against the inside wall of the cylinder, so there would be more pressure inside. When the pressure inside the cylinder becomes greater than the atmospheric pressure outside the cylinder, the gas will expand and push the piston up. As the piston moves up, there is more space in the cylinder, resulting in fewer collisions of gas molecules against the inside wall. And eventually the pressure in the cylinder matches the pressure outside the cylinder, and the gas will stop expanding. Okay, so here's a cylinder, and there's a piston inside of it, and there's a pocket of gas beneath the piston, and the gases, particles are moving around, and it's at sort of a cold, lower temperature. And then if we take this cylinder and we add some heat, the particles are going to start moving faster and faster, which means there's going to be more pressure, and it's going to cause the piston to move up. All right. So as the particles have more kinetic energy, they create more pressure, and it pushes up against the piston, and the volume of the gas increases. So thus, if the temperature of a gas inside the cylinder is increased, the volume of the gas will increase. And this is an example of Charles' law. Charles' law states that at constant pressure, the volume of a gas is directly proportional to its temperature in kelvins. A gas at higher temperature will have a larger volume than a gas at low temperature. If you were to cool a gas, then plot, that's supposed to be singular, if you were to cool a gas, then plot its volume against temperature, you would get a straight line. In the following graph, the volume of a gas in liters is plotted against its temperature in both Celsius and Kelvin. So, here we have a graph. We have volume along the y-axis and temperature along the x-axis. And let's say we were to decrease the temperature. As the temperature gets smaller, the volume also decreases. Now, notice that when the volume of the gas is 0, see the volume here is 2, 1.5, 1.0, 0.5 liters, and now down to 0. So when the volume is 0, its temperature is negative 273 Celsius, or 0 degrees Kelvin. 0 Kelvin is absolute zero. It's the complete absence of kinetic energy. It can't get any colder than absolute zero. The temperature scale gives the true measurement of the kinetic energy of a gas. If the temperature is doubled, the average kinetic energy is doubled, and the volume of the gas will be doubled. And notice that at 273 Kelvin, the volume of the gas is 1 liter, but at double the Kelvin temperature, 546 Kelvin, the volume is 2. So, at 273 Kelvin, the volume is 1, and then if we double the Kelvin temperature, 273 times 2 is 546. The volume changes from 1 all the way up to 2. So the volume doubles when the Kelvin temperature doubles. Now this doesn't work if you use Celsius temperature. If the Celsius temperature increases from 50 to 100 degrees Celsius, the kinetic energy has increased, but it has not doubled. To convert Celsius temperature to kelvins, use the formula K equals C plus 273, where K is the Kelvin temperature and C is the Celsius temperature. So that means that 50 degrees Celsius is really 50 plus 273, or 323 Kelvin, and 100 degrees Celsius is really 100 plus 273, or 373 Kelvin. So a temperature increase from 323 Kelvin, which is 50 Celsius, to 373 Kelvin, which is 100 Celsius, is not a doubling of the kinetic energy. So you can see when you go from 323 to 373, that's not doubling it. Okay, if you were to double this temperature, it would be 600 and something. Well, it's not 600 and something. It's 300 and something. So the temperature is increased, but it hasn't doubled. And I think on here, 50 degrees Celsius, so that would be about here, and then 100 degrees Celsius would be a little bit more, so that would be maybe up to about here. But as you go from here to here, the volume has not doubled. It's gone from 1 to maybe something a little bit more than 1. So that's why we have to use a Kelvin temperature when we do calculations for gas problems, which is going to come up in the next couple of lectures. Okay. For a PDF transcript of this lecture, go to www.richardlouis.com. This has been Chemistry Lecture number 66, Kinetic Theory, Introduction to Boyle's and Charles's Law.